Okay, so in this video lesson, we are going to look at an example to see how we can compare two population mean values. And so let's spend some time reading the description of the problem here. And I apologize for the sketchy description of the example, but it will get better as it's being explained along the way. And so in this example, we are studying about the engineering certifying exam mean score. So any university nationwide here that has an engineering department will offer a what's so-called an engineering certifying exam. That's an exam before engineering students can become formally certified into the major. And so here in this problem, let's say we have two universities. One of them is Newton University, and the other university is Gauss University. And so engineering certifying exam mean score is what we are studying here. And so from Newton University, we found a sample according to the way how the wording is describing here. Then from Newton University, we found a mean value, a mean of 85.5, and these scores are supposedly out of 100. So the mean score from Newton University is 85.5 with a standard deviation of 6.5, where and all these information is from 450 scores that are randomly selected. And so that's the highlighted information. And then the same certifying exam right there, but now when we're looking at the Gauss University students, then we've found the following sampling information. From Gauss University, we found a mean of 80 with standard deviation 5 in a sample of 400 scores that are randomly selected. And so in this example, as a continuation from our general discussion from our general lecture about comparing two population means, then we can draw out some given information as following. The first thing, as I have explained back in the general discussion or the general lecture, is that the main population mean value that we are studying here is the engineering certifying exam mean score. So this is a population mean because really, as I have already introduced earlier, this engineering certifying exam is not only offered at Newton University, it's not only offered at Gauss University, it is offered at any university in the nation as long as there is an engineering department. So this, in other words, this mean score here deserves its place to be a population mean because there are a lot of students in the engineering field. And so now, when we are particularly studying and comparing this mean score from the two schools, one of them is Newton University and the other one is Gauss University, then we are in a situation where we're now gonna break it down to two separate populations. So Newton University is one of them, Newton University, and from Gauss University. And so clearly there are two populations that we would like to compare the respective mean value for. And so just like the idea that I have explained in the general lecture, then now once we realize that we're working on two separate populations, we're trying to compare their respective, we're trying to compare their mean value here respectively from these two different populations. then it is extremely convenient that we are giving a numerical label for each of our population here. And so I can now label this population 1. So it's not really because I favor Newton University over Gauss University, but simply because maybe in my own, and it's just a choice, as I have explained so many times back in the general lecture. So here it's only a choice, and simply for me I made this choice because back in the wording of the example itself, it makes sense that because Newton University was listed first, so I'll just go with that order like that. And so in this way, Gauss University as a population, or Gauss engineering department the engineering department at Gauss University is considered is labeled as population number 2. And so now that means we can regard to this as population 1. And this is population 2. And so now, once the numerical labels were given, then doing that produces the following importance right here. This same mean value, the engineering certifying exam mean score, but now if we're looking for that in population 1, then we are going to call that mu1. And so the subscript 1 here is indicating that this mean is to be calculated. This population mean is the population mean from population 1. Whereas that same mean, but if being found in population 2, we call that mu2. And yes, sigma for population 1 is also labeled as sigma 1, and sigma for population number 2 is labeled as sigma 2. So these are the parameters, the population parameters respectively for on each of our population here. And when it's now time to list down our sampling information, then from population 1, again back on the wording of the example, we have collected a sample of 450 scores randomly selected from Newton University. So this is now population 1. And so pay close attention to the mean and the standard deviation here before I switch back to the writing board here. And so now on the writing board, sample size that I use to collect samples on population 1, now I name that N1. This is 450. The sample mean that I have already found here, that I have already had in hand, that's x bar 1. And this is 85.5. And further, in this sample that we selected from population 1, then we also had a sample standard deviation. And since being from population 1, I give that subscript 1. So S1 here is 6.5. So this is sample standard deviation of the sample that came from population 1. And so now if we're looking over to population 2, the sample that we used, the sample size that we used on each sample from population 2 is 400, according to what's written in the wording description. And so now in 400 scores randomly selected from Gauss University, which is now population 2. And then this mean here is a sample mean value that's from population 2, and this is a sample standard deviation from population 2. And so that means now on this chart right here, on this table, I have x bar 2 equals 80, and S2 equals 5. And so now clearly in this example, just like how I explained back in the general discussion or the general lecture, then N1 and N2 need not be equal. And this is obviously one example out there. Exactly as a reason why N1 is chosen to be different from N2, there can be many different reasons. It could be that the student population from Newton University is a lot more than population from Gauss University, so we have more opportunity to pick a larger samples, whereas in a population 2 over here, at Gauss University, we have a smaller population, so it's only good enough for us to pick about a sample of 400 students. That could be one reason for leading to 2 different sample sizes for 2 independent samples here. And again, we are doing a problem where the samples are independent. And so here, N1, in this case, clearly not equal to N2. And that's obviously being shown in this particular problem here. And so immediately, once we have learned through the general discussion or the general lecture, then recall that a D, or the D value, is defined as the difference mu1 minus mu2. So in this case, it's going to be this value mu1 minus mu2, and it's always going to be a population value from population 1, subtract the value from population 2. That's how we define D. From the beginning here, the labeling, the numerical label from the beginning could have been the other way around. But the definition for D is always mu1 minus mu2. And we also define from the general lecture that a D bar here is simply a sample mean from population 1 minus a sample mean from population 2. So that's just some quick recall from the general lecture. And so immediately after looking back at this definition, then right here from our 2 samples, before I even get into reading the actual question of our problem here, then this is what we know about regarding our 2 samples together here. The 2 samples we've had, the 2 independent sample means we've had, produced for us a D bar value being, in this case, 85.5. This is a sample mean value from population 1. It's only one sample mean value from population 1. And we're subtracting 80. And this is a sample mean value that's from population 2. Our difference here, our current difference that we have in the 2 samples that we're currently having is 5.5 after calculation. So we already had a sampling difference of the 2 sample mean values that we're currently having. And recall further, throughout the example that I worked along with in a general lecture, that eventually in any of our work later, we're going to need to find the combined standard error of the 2 samples. So as a formula, as a quick reminder, it's S1 square over N1 plus S2 square over N2. And the entire expression is inside a square root. And so we can easily substitute in all of these values. S1 for 6.5 for S1, and 5 for S2, and N1 is being 450 here, and N2 is 400 for N2. But I have also developed a little program that's called a DF program that's being shown, that runs with Microsoft Excel as seen on the computer screen right here, that can quickly calculate all the values for us. And so I will come back to this to show how it runs again. So in this way that we will be sooner or later using a technology to calculate the value of the SEC, let's for now hold on to its calculation. And so further recall that since we have 2 samples, we will need to find their overall degrees of freedom. And anyone viewing the lesson here in this particular video must have seen my explanation about the formula for the DF, for degrees of freedom of 2 samples, of 2 independent samples. And so we definitely need to use the DF program that I have developed to quickly find an answer instead of going through the very messy formula. And so now, back on my Microsoft Excel screen right here, S1 here is intended for the sample standard deviation 1. So here I am going to provide 6.5. I will put in 5 for S2, and I will put in 450 for N1, and I will put in 400 for N2. And so now this little portable program of mine now quickly calculated the SEC combined standard error for us, and it also calculated the degrees of freedom. And again, after my explanation from the general lecture that in a way how the degrees of freedom formula was given, which was also mentioned and described in the general lecture, then degrees of freedom here very likely to run into a decimal value like this. But then, so for my class, to ensure that even students with very limited calculator capability can also work with the degrees of freedom, so I asked my own students in my class to use degrees of freedom rounded to the nearest whole value. And so in this case here, our degrees of freedom concluded to be 831. And so the SEC, as calculated from the Microsoft Excel screen earlier, was a 0.39546, and possibly a lot longer. But as I have mentioned before, unless being specified otherwise, usually SEC I'll round to 4 decimal places. So here we're going to use the SEC as 0.3955. So that's our value for SEC, and this is our degrees of freedom. And so this is now all of the given information that we need. First, I made a list of all the given information regarding the samples. And now quickly I calculated these values, because sooner or later a lot of our work will need these values, and they come right out from the sample. So this is what we can prepare ahead of time for us before we get into the actual question. All right, and so now back on the computer screen, now let's continue into reading the actual question of part A of our current example, because earlier we were only reading the general description of the samples that we've had, and these are the given information. Once they are given, they can be used for many different questions of an example. And so here the question is asking, according to the wording, at significance level alpha equals 0.001 are the samples, these two samples. And we have already sketched down the given information as well as some calculations from the two samples given here. So are the samples showing strong evidence that mean engineering certifying exam score of Gauss University is generally less than that of Newton University? So first thing that caught my attention here is that the question brought up a testing hypothesis problem. Are the samples showing strong evidence that, so now the comparison statements here that we're testing as a hypothesis is saying that we want to prove that the mean engineering certifying exam score of Gauss University, mean certifying exam score of Gauss University is generally less than that of Newton University. So according to the wording, mean engineering certifying exam score of Gauss University, as we're seeing again on the computer screen, mean engineering certifying exam score of Gauss University, that is, and right from the wording of the problem, that is mu 2, because currently we define based on our definition of with the numerical labeling, then the mu 2 is our population mean from population 2. And so now we want to show that generally mu 2 is less than mu 1, because that's what it said. That's what it said in the statements here. Mean engineering exam score of Gauss University is generally less than that of Newton University. That of Newton University means mu 1. And so now with this comparison inequality, we can algebraically rewrite this inequality as, in one way, mu 1 minus mu 2 being greater than 0. That's one way to algebraically rewrite this comparison inequality. Or we can also rewrite this inequality algebraically as mu2 minus mu1 to be less than 0. So we have two equivalent algebraic re-expression of this statement. And the point now, the purpose now, as explained in the general lecture, is that we want to rewrite any comparison statement as an inequality statement that involves a comparison between a difference and 0. And then we will choose this form right here because we have already agreed that D, the difference, is defined as mu1 minus mu2. And so now, after investigating carefully at the wording of the question, then now we can come up with our H1 alternative hypothesis. Now it's saying that we're trying to prove that D is greater than 0. Mu1 minus mu2 is a difference that's greater than 0, or simply D is greater than 0. And then from that, we can easily come up with H sub 0, now saying that D equals 0. Again, remind yourself that anytime that we have already recognized an H1, the alternative hypothesis, then H0 is going to be a lot easier to find out by simply rewriting the statement in H1, but replacing the inequality with the equal sign. And so now, in the way how this alternative hypothesis is saying, then this test right here that we're about to do must be a right tail test. And so now, to really get into testing the hypothesis here, then again, the first step here, the starting of our step, is to start out by saying that if we accept H sub 0, so if H sub 0 was true, so if we accept H sub 0 as the truth, H sub 0 was saying D equals 0. So what consequences can be let out from this acceptance? And so also recall from the general lecture that I brought up the idea of what's so-called the extended central limit theorem. And so now if H sub 0 was the truth, or H sub 0 was accepted to be true, then mu d bar must consequently equal 0. We won't have a way to calculate sigma d bar because we never had sigma 1 and sigma 2. And so I'm not saying that sigma d bar doesn't exist. I'm just saying that we won't be able to obtain that value or to calculate that value. So we are not having an available value for sigma d bar. So in that way, we are instead using a closing up approximate for d bar that we call the SEC. And so now recall from our earlier work that SEC was calculated to be 0.3955. And that was the calculation that we have had earlier right from the two samples, right after the moment that we listed down the given information from our two samples. And so once we know that we can use a SEC to substitute as a closing up approximate of sigma d bar, and now along the way we recognize that d bar is a continuous random variable which represents, so I'm saying d bar equal, it represents a difference in an x bar 1 value and an x bar 2 value. So d bar is generally just any difference between an x bar 1 value and an x bar 2 value. And so now realizing that d bar is a random variable, a continuous random variable, and which already had a center at 0 here, then we knew further that the extended central limit theorem says this d bar can be normally, or at least approximately normally distributed with center at 0 and average spread sigma d bar. But again, we won't be able to know the value for sigma d bar. But now once we know that important fact, then we are now quite sure that any sampling difference in an x bar 1 value and an x bar 2 value can be found on a bell curve. So this horizontal line represents all values low to high of our d bar, where the center of this bell curve is at 0. And so we can have some negative difference indicating that sample x bar 1 is less than sample x bar 2, or we can have a positive difference where sample x bar 1 is above sample x bar 2. So now our sample that we are currently having in hand, d equals 5.5. As we have already calculated here, right after the moment that we have listed down the given information regarding our two samples. And so having a d bar value being a positive value, then we know for sure that d bar must stand somewhere to the right hand side of the bell on this bell curve center. And so the next step now is to calculate the t star for our current d bar over here. So again, recall for yourself that t star is our actual value for d bar subtract 0, which is theoretically the center of the bell curve here. And we will be dividing by the SEC. And so continuing into the math problem, then this will be 5.5 minus 0 as a setup and divided by 0.3955. Calculation came out being a positive 13.9064 and a lot longer, but usually I'll just round it. I'll just keep t scores unless being specified otherwise. I'll just round t scores to 3 decimal places. So now that we have had a t score for our calculation, it's a good practice to indicate again that we have already calculated the degrees of freedom of our two samples to be concluded to be 831. So again, I need to remind anyone that for public viewers out there who are viewing this video of mine, then you can use the degrees of freedom in this kind of problem to be a decimal degrees of freedom. But for my students, I ask my students to round the degrees of freedom in this kind of situation to the nearest whole value. So this is how we have our degrees of freedom, 831. And so the next thing to do now is we are going to calculate the p-value for our two samples, which created this sampling difference. So the p-value here, now let's look at the fact that our test here has been decided to be used as a right tail test. And so in a way we're setting up as a way to set up the p-value, the final p-value, we're calculating the probability that on this bell curve we'll find a d bar value greater than or equal 5.5. And so this inequality, which points to the right hand side, is making it consistent with the fact that our test here is a right tail test. This probability problem setup right here is graphically the same as the area that's shaded to the right hand side of wherever our d bar stands in this bell curve. And so now calculating the p-value of this probability, we need to run the LTCDF program to get an approximate, a close enough approximate of area on this current bell curve, because we don't have z-score, but instead we have a t-score. And again, I have to clarify that my LTCDF program will, after running, will give the area supposedly shaded to the left hand side of our current d bar wherever it stands. And I believe many advanced technologies out there can also come with a program or a command that does the similar work, where it finds approximately the area on the bell curve shaded to the left hand side of our sample value with the provided t-score. And so now I'm going to run my LTCDF program. When it's asking for t-score, I am going to provide 13.906, and when degrees of freedom is asked for, I'm going to enter 831. But again, as I said, this answer that comes out from this LTCDF program will only be the area shaded to the left hand side, supposedly on this bell curve. So to achieve the right hand side here, we must subtract the answer from here from 1, and that's how we will arrive at our final p-value. And so now I have developed my own LTCDF program. So let's see how it runs with my program. And again, any viewers who do not have access to this program of mine right here can use any technology that does the same functionality. So my LTCDF program will ask for a t-score. So now we are going to provide 13.906. For degrees of freedom, I am going to give 831. And this is now how much area supposedly shaded to the left hand side of our current sampling difference, where it stands on this bell curve. So the area shaded to the left is already 1. And so now that means our final p-value is 1 minus the answer is supposedly 1, 0.000. And so now that we have calculated our final p-value for this sample, and so the next step now is to compare our final p-value with the significance level that's given in the problem. We want to know whether our p-value is less than or greater than the given significance level. And so now let's look back at our current description of the problem of the example. So in part A, we are given significance level being 0.001, because that's what it says right here. That's what it said. At significance level, alpha equals 0.001. So now apparently this final p-value is to be compared with significance level at 0.001. And so a direct comparison now shows clearly that our final p-value is well below the significance level. And so now, after our experience learning about testing a hypothesis, then anytime we reach to a conclusion saying that p-value falls below the significance level, that means our current sample itself is an unlikely sample. And being an unlikely sample, that will make it a strong evidence. Strong evidence. And the strong evidence here is for us to reject h sub 0. Again, I need to remind, because we started out by accepting h sub 0, and now accepting h sub 0 made our sample here, which we easily obtained, made our sample unlikely sample, and that's now making it strong evidence. So now we have strong evidence to reject h sub 0. Or another way of saying d bar that we have is strong evidence to support h1, the alternative hypothesis. And so now in that way, one more time back to the wording description of our problem. The problem itself is worded as a yes or no question. Are the samples showing strong evidence that this mean engineering certifying exam score of Gauss University is generally less than that of Newton University? So in that case, so now as a yes or no question, for having strong evidence or not, we are having strong evidence. And so now we can ultimately answer yes to our final question. And now, as a closing remark before I'm moving out to the next question in our current example here, then again, be aware that right from the beginning, if I define, or if any of us here who is working on this problem define the two numerical labelings here the other ways around, that meaning this is population 2 and this is population 1, then this statement would have read the other way. D is less than 0, where it would become a left tail test. So again, as a reminder that anytime now that when we are doing comparing two population mean values, then testing the hypothesis as a right tail test or being as a left tail test is just generally a skill that we need to know how to handle. And that so any problem can turn into being a right tail test or a left tail test, completely dependent on how we define, how we gave our numerical label. So it's not simply because the statement in our question here has a word saying less than, then the problem has to be less than. It all depends, and it only depends on how we decide the labeling convention from the beginning. And now let's look at part B of our current example here. So all that given information is retained exactly the same here, and it's being still in the description of our example. So now part B of the example now is asking us to find a 99.8% confidence interval. So again, remind yourself that CI here means, or CI stands for confidence interval. And the purpose of our interval here is to estimate D. All right. And so now, as a brief explanation of how the result we are about to do here in part B will connect with the result we found in part A, let's quickly look at the two hypotheses from part A. From part A, alternative hypothesis was stating that D should be positive, whereas null hypothesis from part A was saying D was equal 0. And we have successfully proven that D was a positive value. We had strong evidence based on our samples. So, but that was all we had. So D bar we had was strong evidence to say that to support H1 saying that this D is positive. But in the end, we still don't know how far this D value is above 0. Is it only a small amount, like a 0.5, or a larger amount, like a 5.5, or something else? And so that's the reason why now we look at question in part B here, where we want to find a 99.8% confidence interval to really estimate D, because now we can come up with an interval with low and high, where this D value can possibly fall in between, and we will have a better picture of where our D value will fall into, rather than just simply knowing that it's a value that's falling above 0. And so now, once we've had all that understanding, then again, I need to remind anyone viewing the video or following along with this video that confidence interval at the very end will ultimately be in a form of a sample value. So it's a very powerful statement here, because sample value, we can either have it as a given information or we can purposely find it. So we will always rely on the corresponding sample value plus and minus a margin of error. And that's how any confidence interval will look like ultimately at the end. And so since our problem here is aiming at estimating the difference of the two population mean values, D, and so the sample value corresponding to that is D bar, and we will be adding and subtracting the margin of error, and so that is how our final confidence interval will look like. And so our D bar has already been found to be 5.5. As we have already laid down all of these calculations before we even got into any of the actual question of our example. And so now from that sample value as the sampling difference of the two sample means, we can just simply find a margin of error to be added and subtract away from this sample value. And so what we mainly use now is the formula for this margin of error. I have given in the general lecture that this margin of error can be calculated by the following formula: T sub c multiply with the SEC. And once again, we have already found our SEC for the two samples right after we have sketched down the given information before we got into any of the questions. And so now it breaks down to only worry about finding this T sub c value. And recall again from our past understanding when we were finding confidence interval, then T sub c is the t-score that's related to the confidence interval, and that's what that subscript c is all about. So let's now spend some time finding T sub c. First of all, recall that our confidence level is given to be c equals 99.8 as given from the question. In the question, find a 99.8 confidence interval. So that means our confidence level is 99.8 for confidence level. But to really use this into calculation, I am going to write that as 0.998. So now first step for calculating T sub c, we are going to go with 0.5 plus half of our confidence level. So 0.998 over 2. Calculation of mine came out to be 0.999, and we refer to this as some left area. Step 2 is to either calculate or indicate the degrees of freedom for our two samples. So now again, that same degrees of freedom we have calculated long before we got into any of the questions is here. This is the degrees of freedom for our two samples together, where 450 is for sample 1 and 400 for sample 2. So that means our degrees of freedom to be used here is 831. The last step is to now finally calculate a T sub c. So we will calculate T sub c by running a command generally known as the INVT command. And most of the times when you run this on any calculator, it doesn't have to be a TI-83 or 84. The INVT command, which is most likely looking like this as well, INVT command, will first thing ask for area left, and after that it will ask for a degrees of freedom. And usually this command is executed with the two values here with a comma between to separate the two values. I have also developed my own INVT program that runs on Microsoft Excel to make it convenient for students in case they don't have any calculator with them that has the functionality here. And so the box that's indicating left area is where we're going to enter 0.999. The degrees of freedom is going to be 831. And so now this is our T sub c value that I made Microsoft Excel automatically calculated for us. And so it's 3.10007, and it could be a lot longer. So as I have said earlier, unless being specified otherwise, usually for T sub c, I'll round it down to 3 decimals. But in this case, we are forced down to only a 3.1. And so now after we have found our T sub c to be 3.1, then our margin of error is ready to be completed. It's 3.1 for T sub c multiply with the SEC that I have shown earlier, which is 0.3955. And so final calculation gave me 1.22605. And in this case, I'll round it down to 2 decimals, so 1.23. Simply because usually these scores are here. Again, we're working with mean scores on engineering certifying exam, which is measured out of 100 points. So it can be equivalent to a percentage as well. And so that's why I use 2 decimal places in what I feel the best precision. But again, when anyone is working on these problems, make sure you watch for your own rounding for the final answer of a margin of error. And that now means our final confidence interval is found as following, from where our sample value being the sampling difference 5.5, we are going to add and subtract from it 1.23. And this is our confidence interval. This is the margin of error. And so the way how it says now is that guaranteed at successful level 99.8%, or guarantee at 99.8% chance of successful, then the actual difference in the two population mean values is going to be somewhere up and down by 1.23 from 5.5. And again, since being a confidence interval, being an interval, we can subtract this margin of error from the center point, from the sample value in the middle, in the center, to come up with low end. So alternatively, we can write the low end to be 4.27, and the high end can be found by adding 1.23 with 5.5, which gives us 6.73. And so again, this interval, this format of the interval is referred to as the traditional format. Of the interval, because it shows a low and high. Again, at confidence level 99.8, which guarantees that successful at 99.8% chance, then this difference between the two population means will be anywhere inside of this interval between the low and the high given here. And now we are at part C of our current example. And so again, all that same sampling information remains the same. Here we are at our question C here, which is asking, at significance level 0.001 are the samples showing strong evidence that mean engineering certifying exam score of Gauss University is generally other than that of Newton University. And so aside from this term other than, which is different from part A, then this question really is a repeat of problem A that we have done. So first thing to be clear again, I will stay in the same numerical labeling convention of how I started before we got into question A. And so this is how the given information is listed here on the board regarding the two samples being selected from the two populations, 1 and 2. And so from the sampling information listed here, we found for ourselves the D bar value calculated previously to be 5.5, which will be used again in this coming problem, testing a hypothesis. And we also already calculate SEC, and that will be used again in our coming problem right now. And as well as the degrees of freedom being 831 for the two samples combined together, where N1 is at 450 and N2 is at 400. And so now back in the wording of the problem, are the samples showing strong evidence that mean engineering certifying exam score of Gauss University. So mean engineering exam score of Gauss University. This is mu 2 according to our labeling convention. And so with the wording again to be continued here, we want now to say that mu 2 is generally other than that of Newton University. So that of Newton University here means the mean engineering certifying exam score of Newton University. So we want to prove now that mu 2 is other than mu 1. And so again, algebraically, this comparison statement here can be rewritten as mu 1 minus mu 2 to be other than 0. That's one way of how we can rewrite that. Or we can also rewrite the same comparison statement here as mu 2 minus mu 1 is other than 0. However, since we have learned previously that we defined D as the difference between the two population means to be mu 1 minus mu 2 for whichever is taking the role of number 1 and whichever is taking the role of number 2. So in that way, we are going to stay with this particular written form to make it consistent with our definition. That is D equals mu 1 and mu 2. And so now back to the actual question itself. And now I just once again want to point out that the question here itself is bringing up for us a testing of a hypothesis problem, or the samples showing strong evidence that etc. and etc. And so now realizing that we're having a testing of a hypothesis problem, then the first thing is to identify our hypothesis. Our alternative hypothesis is the easier one to find. And just like what I was addressing earlier, now we're looking at D is, we're trying to say in our H1, the alternative hypothesis, D is other than 0. And now once we have had H1, then H sub 0 can be easily written as D is equal to 0. And so our problem that we're doing here will be a two-tail test. And for this example, for this part of the example, I am going to pick up the pace a little bit because as we progress through the problem, anyone viewing the video will notice that really over 90% of the structure of the problem will remain exactly the same, except for the only difference between now and what we did in part A is we switched from a right tail to now a two-tail test. And so again, I'm starting out with saying if we can accept H sub 0, if H sub 0 was accepted in the beginning. So formally speaking, if H sub 0 was true, saying that D equals 0, then in that way, extended central limit theorem guarantees for us that mu D bar must be equal to 0, because mu D bar theoretically equals D, which is accepted for now equals 0. We won't be able to calculate the value for sigma D bar simply because we do not have the values for sigma 1 and sigma 2. But that doesn't mean sigma D bar does not exist. It's just we won't be able to, and we're not able to find the actual value of sigma D bar. So instead, we're going to be using SEC to substitute for sigma D bar, and SEC is usually a close enough approximate of sigma D bar. And so recall from earlier questions and problems that SEC, our combined standard error, was calculated to be 0.3955. And then again, just a reminder for anyone that our sampling difference of the two sample means is just one among infinitely many other sampling differences between a sample mean from population 1 and a sample mean from population 2. So in other words, the d bar we have here is a random variable, a continuous random variable that represents about a difference in an x bar 1 value and an x bar 2 value. And so we further would know from the extended central limit theorem, even though without a formal explanation, that d bar will usually be on a bell curve. D bar is normally distributed, with the center would be at 0, the value that we accepted to be d, and average spread sigma d bar. And so now we can imagine that our d bar will stay on a bell curve, where anywhere left and right of this horizontal line is a possible value of the d bar existing out there, of the random variable d bar. So center of this d bar is at 0. So our particular d bar that we have calculated equals 5.5, which must be somewhere on the right hand side, to the right hand side of the bell curve, center 0 over here. And so in that way, the next step now, I am going to calculate t star. And to do that, my d bar value, subtract the center of the bell curve being 0 at the moment in this case, and divide by the SEC, which is 0.3955. And so as I keep progressing forward, then anyone viewing this lesson here, this particular problem here, is realizing that the structure so far is exactly the same as the steps you have seen back in part A of the current example. And so that's the reason why I'm saying that we can pick up the pace here. So now this is 13.906 for our t star value. But now for this problem, to prepare for our next step, to start treating the problem as a two-tailed test, then I am going to clearly indicate that our t star here is a positive value t star. And then instead of calculating the degrees of freedom, here we already had the degrees of freedom calculated, so here I'm just going to simply indicate it that here again. Our degrees of freedom for the two samples here is going to be 831. And so now after we've had degrees of freedom, now we can start calculating our p-value. So in this way, if we're accepting h sub 0 to be true, then our sample value here being the d bar will have the following p-value as a consequence. And the p-value will be set up as the probability where we can find a d bar greater than or equal to 5.5. And so I had to clearly indicate this positive sign for our t star, because when we actually run into the p-value calculation setup as a probability, knowing that our t-score is a positive, then I'm going to set up a right tail probability calculation. And then being a two-tail, now we are going to multiply this overall probability problem by 2. And that is why it's important that anytime we're doing a two-tailed test, make sure to indicate the sign of your t-score, or maybe in other cases, z-score. And that sign will lead to deciding whether to use a left tail or a right tail, like the inequality in this case. Then being a two-tail, we will multiply the overall probability by 2. So as we have seen in earlier part of this example, in part A specifically, then to find this probability, I am going to run my LTCDF program or some equivalence technology or software program that can find the area on this bell curve, which is for now shaded to the left hand side of our sample. And so our sample has t-score 13.906, and the degrees of freedom that my LTCDF program or any equivalent technology will ask for is to be given as 831. But again, LTCDF will only give you the area shaded to the left hand side of where our sample stands. But here, since the inequality here is indicating right tail, that means we are actually looking at this area shaded to the right hand side of where our sample stands. So to be a right tail area, we need to subtract the answer from the LTCDF program from 1. And now being a two tail, I'm going to take all that answer and multiply by 2. And quickly on my computer screen here, again, LTCDF program that I developed, and it will be the same if you use any other equivalent program. But the area shaded to the left of t-score 13.906, or about approximately the area shaded to the left of 5.5 on this bell curve, is according to the calculation you have seen earlier on the computer screen. On this here is 1, but 1 being subtracted from 1, and we multiply that by 2. So our final p-value is calculated to be as a 0. And so now that we've found our p-value to equal 0.0000, so the next step in testing a hypothesis always is to compare our final p-value with the given significance level to find out whether it's less than or greater than the given significance level. So back on our lecture notes here, back on our computer screen here, then we had significance level given at what's indicated here, alpha equals 0.001. And so now we can compare our final p-value with the given significance level at 0.001. And clearly, this final p-value of ours falls below the significance level. And that is now enough to make the conclusion that the sample value that we have as a sampling difference between the two sample means itself is an unlikely sample. And that leads to our sample value is showing strong evidence, or itself is strong evidence. To, on one hand, say that we are rejecting h sub 0. Or, on another hand, we can say that we can support h1. And ultimately, as a yes or no question, as stated here, are the samples showing strong evidence? We here now just verified that we've had strong evidence from our sample value. Then ultimately the final answer for this question is yes.